Natural physics is a concept astrophysicist LeRoy developed that explains in down-to-earth scenarios how the principles of physics could have come about from observing nature. Each episode begins with a scenario, followed by an example to illustrate the application of these principles in futuristic research at the frontiers of science, such as LeRoy's astrophysics doctoral research, and then concludes with an exploration of how these same principles could have very well been used by ancient cultures and civilizations. Mathematics is naturally encountered and incorporated as the exciting and fun tool of science that it is. Science is the window into our amazing world of nature, and mathematics is the tool to open that window. Natural physics encompasses current, futuristic, and ancient physics, and ties them together by the principles of physics that are common threads running throughout each.
Greetings, I'm LeRoy, and welcome to the Natural Physics Experience, live from Costa Rica. The last show we left off where we had derived the 4x4 matrix that describes the effect that a quadrupole magnet has upon the protons as they accelerate around the synchrotron at Fermilab. Okay? I talked about having a toolbox, okay? And I'll show you that right now. As I said before, imagine we have a toolbox with all of these different mathematical tools that we're using to track the motion of the protons around the synchrotron, right? A lot of tools, hammers, screwdrivers, drills, right? Tape measures, okay? We started out with analytic geometry, which is a combination of algebra and geometry, okay? We brought in calculus, all right? We had trigonometry in the mix, okay? And we had differential equations and partial differential equations, all of these tools. And then lo and behold, we get to linear algebra, which uses matrices to describe physical phenomena. We made an analogy between optics, which is dealing with light, and high energy physics, right? With optics, you're using lenses, concave, convex, to transport a beam of light, which is photons, right? Remember, photons have no mass. They're particles of light. They travel at the speed of light, 186,000 miles per second, not per hour, per second, which is equivalent to 300,000 kilometers per second, okay? But in the case of the quadrupole magnets that are used to focus the beam of protons, protons have a mass, okay? They have a mass. And so you have the same principle going on because protons are charged. They react to a magnetic field, okay? Just like electrons would. Photons? No. Not only do they not have a mass, they don't have a charge. And they clock along at the speed of light, okay? The protons that are accelerated in Fermilab, they're accelerated at very high speeds, okay? Approaching the speed of light, but not quite there. Now, As I've said before, the cosmic rays that reach us from outer space, their energies are magnitudes greater than the energy of the protons that we're able to produce here on Earth. Okay? Both are traveling at close to the speed of light, but the energies are different. Okay? The energies are different. Cosmic ray energies are huge compared to what we're able to accomplish here on Earth. And so, back to the matrix of the protons as they circulate around the synchrotron. And notice, again, I make this a comparison to cosmic rays. Okay? What in nature is serving as a 4x4 matrix, right? To simulate the effect of a magnetic field on these protons, okay? All right. Okay, so where we left off, all right, we have derived the equations of motion of the protons in phase space. Remember, phase space, that's the area perpendicular to the trajectory of the protons around the synchrotron, right? X direction to the left and right, Y direction up and down. Okay, that's phase space. Okay, and here's a diagram that I made in an attempt to describe phase space. Remember the betatron oscillations of protons around the synchrotron, simple harmonic motion, right? They go left and right, up and down like a spring around that central trajectory through the quadrupole magnet, okay? Simple harmonic motion, right? Okay? A key into nature. There's certain motions that go on in nature that can be described as simple harmonic motion, like a spring, right? There's certain motions that go on all around us that repeat themselves, okay? When you find that pattern, that here's a phenomena that repeats itself, you can pull out that tool from the toolbox and say, okay, this is simple harmonic motion. Okay, so let me use the appropriate tool to analyze this phenomena. Now that I have determined that it repeats itself, it's periodic, it's simple harmonic motion. Okay, all right, so back to the protons circulating around the synchrotron. They have a periodic motion like a spring, back and forth, up and down around that central trajectory. And so we were able to use the mathematical equations that describe simple harmonic motion. And that involved calculus, it involved trigonometry, okay? And we manipulated the equations and that involved algebra, okay? Now, I'm going to show you this diagram of phase space that I made, phase space ellipse, okay? And you'll see that as an ellipse, the motion is going to repeat itself, just like a circle, okay? And it shows the x-axis and the y-axis with respect to that central z-axis, okay? And think of that diagram I showed you before of the spring going up and down, okay? Very similar, right? One is showing an object going up and down with a spring attached to it, and it's periodic. It has a maximum amplitude up and down as far as it's going to get. The same thing with the phase space Betatron oscillations of the protons as they go around the synchrotron. They're going to have a maximum amplitude to the left or to the right, right, horizontal to that central z-axis, and they're going to have a maximum vertical amplitude up and down with respect to that central z-axis. Okay, so very similar. The spring and the phase space ellipse both represent a pattern, periodic motion that repeats itself. One is in the case of an object connected to a spring. The other one is the case of the protons undergoing Betatron oscillations as they circulate around the accelerator. And now, a very important quantity to derive as we continue on is the force constant, K, in those equations that you've seen, okay? It's called the force constant. And back to that spring with the object connected to it, the force constant can be thought of as how tight the spring is, right? How tight or how loose, okay? And with a spring, you can imagine, yeah, very tangible how tight, how loose the spring is, okay? Now, let's go over to the quadrupole magnet. We have a magnetic field. Just like the spring, it has a force constant that's connected to how much it is going to influence that proton as it goes through the quadrupole, okay? A force constant, right? Just like a spring. But instead of being a physical spring, tightly bound or looser, the quadrupole's magnetic field, the strength of it, is connected to its force constant. How tight the magnetic field of that quadrupole is, or how loose it is, okay? So, what's very important, now that we have gotten to the 4x4 matrix from linear algebra, another tool from the toolbox, now that we have gotten to the matrix of the protons as they circulate around the synchrotron, okay? We have to find out what that force constant is of the quadrupole magnet, right? We got to get a number. Yeah, we have a mathematical representative of it, but we got to get that number for our situation, okay? For the synchrotron, right? Just like back to the spring with the object, there's experiments you do that you can determine that force constant of that spring. Well, we're going to have to do the same thing with the quadrupole magnets. We got the equations of motion. We got the matrix that represents a quadrupole magnet, whether it be radially focusing, axially defocusing, or radially axially focusing, radially defocusing. We got that 4x4, right? And there's that K in it that we got to find out what that is. We got to get a number for that, okay? So we're going to get our toolbox, and we're going to use some more mathematical tools to determine this physical quantity, this force constant that the magnetic field of a quadrupole magnet in the synchrotron, what this force constant is, okay? So that's going to be our next step, all right? We're taking it bit by bit, all right? So that's what we're going to do, and just a little inkling into what's coming up. To get an idea of where to begin to find this force constant, we're going to have to go back to optics, okay? We're going to have to use the analogy between optics and high energy physics, between lenses that are used to focus a light beam and quadrupole magnets that are used to focus a beam of highly energetic protons, okay? We're going to have to do that. And from optics, the approximation is called the thin lens approximation. So we're going to pick this back up, but with respect to the quadrupole magnets, okay? A lot of mathematics. And this approximation is just to get an idea of where to start. Sometimes you just have to start somewhere, right? Just so you can get going. And that's what this is about, this thin lens approximation that's going to be used so that we can get a handle and a start on how to find the force constant of the quadrupole magnets in the synchrotron. Okie dokie. Tune in next week, same fat time, same fat channel.